Hello children, how are you all? Hope you all are doing well. This is Krishnamurthy. You can call me as VKM. Welcome to Electron Chemistry Center. Hope you all are doing well. And first of all, I wish you very happy New Year. I am doing this video on January 1st. That's why I am wishing you a very happy New Year. And in the last session, we have discussed about class 12 topics. Since long time, I have not done any class 11 topic. That's why in this video, I am going to explain about the topic from class 11 of physical chemistry. The chapter name is chemical equilibrium. Chapter name is chemical equilibrium. And the topic from the chemical equilibrium, what I am going to discuss it in this session is law of mass action. Law of mass action, or else you can call it as law of chemical equilibrium, or else you can call it as law of chemical equilibrium, law of mass action, or law of chemical equilibrium. It was proposed by Guldberg and Vage. These were the two scientists proposed law of mass action or law of chemical equilibrium, right? So according to this law, what is the statement can be given? Let's see. The statement is the rate of a reaction at a given temperature, the rate of reaction at a given temperature is directly proportional to rate of reaction at a given temperature is directly proportional to active mass or molar concentration of the reactants. Molar concentration of reactants. So the rate of reaction at a particular temperature or at a given temperature is directly proportional to active mass or molar concentration of reactants. It is the statement of law of mass action. If you consider an example, that is A is giving rise to products, then rate of reaction is directly proportional to, active mass of the A. Active mass can be represented, or concentration can be represented with square brackets. So rate is equal to, if you remove the proportionality symbol, we can keep K. So K into concentration of A. So this is the rate law or rate expression can be given. Similarly, you can take even X moles of A and Y moles of B are reacting with each other and giving products. So in that cases, rate of reaction is directly proportional to active mass of A, and whose stoichiometric coefficient, what is the stoichiometric coefficient here? X can be raised to the power, and similarly concentration of B, whose stoichiometric coefficient is Y raised to the power. So if you remove the proportionality symbol, you can keep is equal to, so you can place constant here. So K of concentration of A raised to X and concentration of B raised to Y. So this is the rate expression or rate law can be given for this equation by using law of mass action. That mass action name indicates very clearly active masses. Rate is directly proportional to the active mass of the reactants or initial concentration of the molar concentration of the reactants, we can say. And still, so if you go into the deeper understanding of it, right, how can you give the expression for the equilibrium constant based on the law of mass action? Let's make a look on it. So we are going to derive equilibrium constant expression. So I am taking A moles of A, B moles of B is in reversible with C moles of C, D moles of D. C and D are, A, B are examples of reactants. C and D, capital letters, are examples of products. Capital C, capital D, and capital A and capital B. But we have A, B, small letters. These are stoichiometric coefficients. These are stoichiometric coefficients. These are stoichiometric coefficients. So now, according to law of mass action, for this reversible reaction, how can you give the expression? So I'll be taking, it is a reversible reaction, right? It is a reversible reaction. Now for forward reaction, we will be considering first forward reaction. For forward reaction, if you take forward reaction, what is the forward reaction we have, children? A moles of A, B moles of B giving rise to C moles of C, D moles of D. So rate of reaction is directly proportional to concentration of forward reaction, right? Concentration of A raised to A, concentration of B raised to B. It is the expression can be given based on law of mass action. So rate is equal to K into concentration of A raised to A and concentration of B raised to B. Here we can write it as Kf. We can write it as Kf, and this rate I can write it as Rf, where Rf stands for rate of forward reaction. Rf stands for rate of forward reaction. Similarly, Kf, okay, Kf if you take it, then it is equilibrium constant. Equilibrium constant for which reaction? Forward reaction. So equilibrium constant for forward reaction can be indicated as Kf. Don't keep G in the middle, it will become Kgf, that's why. Okay, so Rf is equal to Kf into concentration of A raised to A into concentration of B raised to B. This is the expression can be given for rate of forward reaction. Similarly, if you take for backward reaction, similarly you can take it for backward reaction. So for backward reaction, so what is the backward reaction? We have C moles of C plus the D moles of D is giving rise to A moles of A plus B moles of B. Then rate of backward reaction is directly proportional to concentration of C raised to C, concentration of D raised to D. So then rate is equal to K into Kb. So rate is equal to Kb into concentration of C raised to C, concentration of D raised to D. So this rate can be taken as Rb, that is rate of backward reaction. So rate of backward reaction is equal to Kb into concentration of C raised to C into concentration of D raised to D. It is Rb stands for rate of backward reaction. Rb stands for rate of backward reaction, whereas Kb stands for equilibrium constant for backward reaction. Kb stands for equilibrium constant for backward reaction. Children, hope you are following it. It is equilibrium constant for backward reaction. Very simple it is. Now, based on this, we are going to derive an expression for equilibrium constant. At equilibrium, we know at equilibrium, if we take it, at equilibrium stage, rate of forward reaction is equal to rate of backward reaction. Both the rates are same. Forward and backward reactions occur at the same rate at equilibrium. So Rf expression what we have, children? Kf into concentration of A raised to A, concentration of B raised to B. This side Kb of concentration of C raised to C, concentration of D raised to D. Right? Then Kf upon Kb. Kb sent it to this side, and concentration of C raised to C, concentration of D raised to D upon concentration of A raised to A, concentration of B raised to B. So this is what we got it expression. Kf is a constant. Kb is also constant. Yes or no? Kf is a constant, Kb is also constant. Both are constants. Ratio of two constants will give you another constant. So here Kf upon Kb, that I can take it as, observe it carefully, I am giving it in new slide. So here Kf upon Kb can be taken as a Kc, can be taken as a Kc, right? So this Kc is a equilibrium constant. Kc is equilibrium constant for concentrations. For concentrations. For concentration, we can take Kc. So Kc, what is the expression then? Concentration of C raised to C, concentration of D raised to D upon concentration of A raised to A, concentration of B raised to B. So in the numerator part, we have products concentration. In the denominator part, we have reactant concentration, whose stoichiometric coefficients are raised to the power. So Kc is equilibrium constant for concentrations, that can be defined as, Kc is defined as, how do you define Kc? It is the ratio of Kc, it is the ratio of product of, means multiplication, product of concentrations of products, concentration of products to the product of, to the product of concentration of reactants, to the concentration of reactants and their stoichiometric coefficients, both products and reactants of course, and their stoichiometric coefficients raised to the power, stoichiometric coefficient raised to the power. If their stoichiometric coefficients raised to the power, and then it is said to be Kc, what it is called as a Kc. But if you would like to use it for gaseous system, for gaseous system, right, instead of concentrations, partial pressures are used. Partial pressures are used. Partial pressures are used instead of concentrations. So instead of concentrations, we can use partial pressures. Then Kp will be, Kp is nothing but equilibrium constant for partial pressures. So here instead of concentration, what I can take it, partial pressure of C raised to C into partial pressure of D raised to D upon partial pressure of A raised to A into partial pressure of B raised to B. So this is the expression can be given, expression for Kp, where Kp is equilibrium constant, equilibrium constant for pressures or partial pressures you can say. So like that we have two types of equilibrium constants. One is Kp and another one is Kc. Kc is meant for equilibrium constant for concentrations. Kp is meant for equilibrium constants for pressures. Hope you understand. Now we are trying to relate both these Kp and Kc. So the next topic what we are going to talk about, it is relation between, what is the topic children? Relation between Kp and Kc. Relation between Kp and Kc. How do you relate them? Relation between Kp and Kc. It can be related by using ideal gas equation. Ideal gas equation is PV is equal to nRT, right? PV is equal to nRT and pressure is equal to N upon V into RT. This N upon V can be taken as concentration, that is C into RT. So that C is equal to N upon V. This can be taken as active mass. Whenever they ask you to find it out active mass, we have to take a formula, that is number of moles upon unit volume. C is equal to N upon V. Hope you understand. So P is equal to, what we got it children here, P is equal to C into RT. P is equal to C into RT, where C stands for concentration, R is universal gas constant and T is temperature. But if you take an expression, that is same expression, I'm taking it once again, whatever we have taken so far, AA plus BB reversible with CC plus DD. So now what is the Kp expression can be given for this? Partial pressures of C raised to C into partial pressure of D raised to D upon partial pressure of A raised to A into partial pressure of B raised to B. But we have formula for pressure, right? What is the formula? We have C into RT. C stands for concentration, right? So it can be Kp is equal to concentration of C raised to C, concentration of D raised to D into RT whole raised to C plus D. Sum of that concentration terms, because RT raised to C into RT raised to D you will get it. Yes or no? That means A raised to M into A raised to N is equal to A raised to M plus N. That is what I have written, direct equation, divided by partial pressure of A, partial pressure of B. C into RT you have to take it, right? So concentration of A raised to A, concentration of B raised to B. So RT whole raised to, what you will take it here? A plus B. But we know this whole expression is nothing but Kc, right? Check it. Kp is equal to Kc into RT whole raised to C plus D minus A plus B, because it is in the form of A raised to M upon A raised to N, which is equal to A raised to M minus N. This C plus D is nothing but sum of number of moles of products, right? Gaseous products. A plus B is nothing but sum of number of moles of reactants. So that I can take it as a delta N, where delta N is equal to C plus D minus A plus B. Delta N can be given as number of moles of gaseous products minus number of moles of gaseous reactants. So instead of this C plus D minus A plus B, you can write an expression that is Kp is equal to Kc into RT whole raised to delta N. This is the relationship can be given between Kp and Kc. Hope you understand. If you understand, please post it in the live chat. Say yes or no. Kp is equal to Kc into RT whole raised to delta N is the relation between Kp and Kc. Based on this, so many questions they will ask you. So here delta N I have told you. Based on equation, we have three cases. Case 1 is delta N if it is equal to 0. Delta N if it is equal to 0, that means difference in the number of moles can be taken as 0. In that case, what will happen? Kp is equal to Kc into RT whole raised to 0. A raised to 0 will be equal to 1. So Kp is equal to Kc. Both the values are same when delta N is equal to 0. Case 2. Case 2 is delta N greater than 0. Delta N greater than 0 in the sense, children, what it is? Positive, right? So delta N greater than 0 means positive. So Kp is equal to Kc into RT raised to 1. 1 means positive, of course. So obviously Kp is product of Kc and RT. That means Kp will be greater than Kc. Kp will be greater than Kc. Take an example. For first case, I am taking an example here. See, 2Hi reversible with H2 plus I2. Delta N, number of moles of products will be 2. Number of moles of reactants will be 2. 2 minus 2 will be equal to 0. Delta N is equal to 0. So if delta N is equal to 0 means for this reaction, Kp is equal to Kc. For this reaction, Kp will be equal to Kc. Such a way they will ask. In the similar way, you can take an example. PCl5. Second case, I am writing example here. PCl5 reversible with PCl3 plus Cl2. Number of moles of products will be 2. Number of moles of reactants 1. So delta N will be equal to 2 minus 1, which is equal to 1. So here in this case, delta N is greater than 0, positive. So obviously Kp greater than Kc. Kp can be taken as greater than Kc. Hope you understand that. Such relations they will ask based on equations, especially for CET examinations, children, especially for CET exams, right? So now let's take case 3. Case 3. Case 3, if you observe it, delta n less than 0. Delta n less than 0. So if delta n less than 0 in the sense that can be taken as negative. Then if it is negative means Kp is equal to Kc into Rt whole raised to minus 1. So that can be taken as Kp is equal to Kc. Rt raised to 1 minus 1 means 1 by Rt. That means Kp value will be Kc upon Rt. That means Kp value will be less than Kc. Kp value will be less than Kc. So it can take an example here, right? So N2 plus 3H2 reversible with 2NH3. So delta N, number of moles of products 4, reactants, number of moles of, just wait, number of moles of this products can be taken as 2, reactants will be 4, 2 minus 4 minus 2, we got negative, so Kp will be less than Kc. Hope you understand, children. So I'll give you expressions, a few reversible reactions. You have to write down the Kp and Kc expressions. You have to write down the Kp and Kc expressions. For suppose if I take an example, H2 plus I2 reversible with 2HI. What is the Kp expression? Kp will be partial pressure of Hi whole square upon partial pressure of H2 into partial pressure of I2. That is a Kp expression. Similarly, what is the Kc expression can be given? Concentration of Hi whole square upon concentration of H2 raised to 1, concentration of I2 raised to 1. This is the way. Product concentration upon reactant concentration. Stoichiometric coefficients anyway raised to the power. Stoichiometric coefficients raised to the power. Now similarly, you can take one more example. PCl5 reversible with PCl3 plus Cl2. Kp expression is partial pressure of PCl3 into partial pressure of Cl2 upon partial pressure of PCl5 can be taken. Similarly, what is the Kc expression can be given, children? Guess it. Concentration of PCl3 into concentration of Cl2 upon concentration of PCl5. This is the expression can be given. And take one more example. CaCO3 is in reversible with CaO plus CO2. This is solid. This is solid. This is gas. So now if I write Kp expression, Kp will be equal to partial pressure of CO2. That's all. We are not going to take solid. Solid concentrations and pressures can be taken as 1 always. Unit molar concentrations. Solids cannot be considered. So here partial pressure of CaCO3, partial pressure of CaO can be taken as unity 1. We are not supposed to take it, right? Unit molar concentrations only you have to take it. And similarly, you can take another example, NH4HS. It is solid, reversible with NH3 gas plus H2S gas. For that, if I ask you to write Kc, Kc is equal to concentration of NH3 into concentration of H2S. That's all. Because this NH4HS is a solid. So whenever solid is there, its molar concentration should be taken as 1. Its molar concentration should be taken as 1. Hope you understand. So this is the expression can be given for Kc. Is it clear? So in this session, we have discussed about law of mass action and Kp, Kc expressions, relation between Kp and Kc, how the different cases when delta and value varies, and how do you write the Kp and Kc expressions for various equations. Hope you understand. Hope you have enjoyed the session. Is that clear? If you like the video, please click on the like button. Don't forget to like. And if you have any doubts, you can post it in the comment box. And if you haven't subscribed to my channel, please subscribe to my channel. And if you have already subscribed, please click on the bell icon. Don't forget to click on the bell icon to get the notifications. So if you have Any requirement for your videos, please post it in the comment box. I'll definitely do it, right? So we'll catch up in the next video. Until then, take care. Signing off. Bye. Thanks for watching the video, children.